Hi everyone, I am the first author of our paper, DeepDualMapper, a gated fusion network for automatic map extraction using aerial images and trajectories. Thanks for coming, and we're sorry that we cannot attend the conference due to the unfortunate situation of novel coronavirus. So we make this video to introduce our work about this paper. The main task is the automatic map extraction, and the mission is about extracting useful road structure information to form a digital map from some data sources. The critical issue is how to gather real-time map data in an automatic way accurately. In this paper, we focus on two data sources, the aerial images and the GPS trajectories. The aerial images are captured by satellites and are publicly available in many places. For example, Google Earth could keep aerial photographs up to date and have been explored extensively in the past decades for map extraction. The GPS trajectories capture human movements in the urban area. As we know, most human actions are constrained by the underlying road network. However, neither data source is perfect for automatic map extraction because of the information loss issue. Missing information in the data is inevitably, and it is exceptionally challenging to infer the map accurately. As shown in the figure, the first column is the aerial image. In the top picture, some road is occluded by trees and the road is hard to extract from the image. For another case, the second column is the GPS trajectory data. In the bottom image, some less popular roads have very few, even zero, historical trajectories. Such information loss introduces more complexity to the automatic map extraction task. So, it is natural to think of that if we could find an effective way to combine two data sources and make full use of all information, the information loss problem can be addressed. In the current literature, a variety of researchers have tried to fuse aerial images with other auxiliary data sources. However, these approaches either concatenate the features of two modalities directly, or just compute the average of all predictions made by each modality. We argue such rough designs fail to fully explore the utilities of both modalities and are not able to effectively address the issue of information loss faced by both modalities. Consequently, we propose a novel fusion model, namely DeepDualMapper, which aims to fuse the aerial image and trajectory data more seamlessly. We design a gated fusion model to explicitly learn the modality selection based on the confidence of each data source. We also introduce a refinement process conducted through the densely supervised refinement strategy to refine the prediction generated by the gated fusion module from core to fine using residual refinement learning. We adopt two unique convolutional encoder modules as two streams to get the features extracted from two modalities. Then, the features are fused to become more trustworthy and more valuable to infer the answer by a gated fusion module. Then we use the fused information from the gated fusion module as an input, put it into a new refinement decoder to predict the map. The decoder refines the fused information with dense supervision. We first introduce the gated fusion module. The module is proposed to simulate the human decision-making process. We denote F as the feature representation of one modality. The subscript mark indicates different modalities, the I for aerial images and T for trajectory data. A is the adaptive feature, and it's in a shared representation space transformed from F, and it also shares the same subscript mark with F. Since when we fuse two different modalities, we need a unifying representation in a shared space. The superscript I of all marks indicates the level of layers in the UNet decoder structure. Then we introduce two gates controlling the information flow based on the predictability of each modality. GI and GT refer to the gate values of aerial image and trajectory. As shown in the figure, following the arrow, the gated fusion module takes the activation maps from two modalities as input. Fi for aerial image and Ft for trajectory are inputs, and the fused features AF are the output. The adapters transfer the activation space Fi and Ft to a uniform space A, and it enables a linear combination of the two activation maps in such a uniform space. After the transformation, the activation maps are both in one uniform space, and they can be safely fused by a linear combination. So the complementary constraint equation Gi plus Gt from level I equals to 1 enforces the module to learn a complementary style fusion. It implies if a certain area in one modality has higher confidence when generating the prediction, then it will assign a larger weight to this modality and simultaneously reduces the weight of the other modality. The submodule selector computes the gate values Gi and Gt based on the information of two modalities. And at level I, the decision of the gate is based on the decision made at level I-1 with some residual refinement delta G. The intuition is that we want to perform a consistent regularization on the gate decision space across all scales. The densely supervised refinement decoder is to further process the fused information into the prediction map. We will introduce it in two parts: the refinement style decoding and the dense supervision. The first part is the refinement style decoding. As shown in the figure, we refine the fused feature from coarse to fine. First, both image and trajectory modalities make their own independent predictions. Next, the gated fusion module fuses these two data sources by enlarging the one being more confident to predict the answer, which leads to a more precise prediction. However, we can observe from the figure, such a linear combination may still face some issues like isolate tiny roads and the unsmooth predictions. Then, the decoder utilizes the fused feature AF as the base and learns some area invariant refinements, such as smoothing the predictions and removing the isolate points and short branches. Such a fusion refinement process is consistent with our intuition. Inspired by the residual refinement learning, we directly leverage the fused feature as the base of the feature map, and we want the decoder to learn a residual refinement of AF. The red part is the residual refinement function. The refinement decoder still follows the elegant structure of UNet, including 4 decoding blocks composed by a stride 2 deconvolutional layer for a learnable 2x upsampling and 2 3x3 convolutions. Concatenation is adopted to combine the information upsampled from the previous level and the information from the current level. The second part is the dense supervision. First, adaptive features AI, AT, AF, and AR should remain representation space consistency because of the adapter modules and the linear operations like the combination and the residual addition. So we force the representation space of them to be the same one by putting them into the same prediction module. Accordingly, we decide to adopt a shared prediction module that takes the features in space A as input and produces a binary prediction. We use the prediction of the refined feature AR in the last level of the decoder to be the prediction in inference time. We use 3 real city scale datasets for experiments, including Porto, Shanghai, and Singapore, containing aerial images from Google Map and text GPS trajectories. For the consistency of the form, we convert the trajectory points into an image by drawing them on a map. Some dataset details are listed in the table. We get railroad structure from the OpenStreetMap website and also turn the topological data to binary digital map images. So for the same location, we have 3 different data in image format describe it. As you can see, we use error images and trajectory images as data sources, and the binary digital map images as the ground truth. And you could also see The global visualization of 3 data sets. The area in green square is the validation set. The area in red square is the test set. All rest areas serves as the training set. We evaluate the performance of different approaches in extracting the maps from 3 cities and the test regions. The results are reported in the table. In general, fusion-based approaches outperform all approaches using trajectories or aerial images only. The combination of data sources complement each other can significantly improve the overall performance. Our method, DeepDualMapper, demonstrates its superior performance, as it consistently outperforms all competitors in all 3 datasets. Note that DeepDualMapper achieves a much stabler performance as its standard deviation tends to be small. We also show the correlative results with the area size of about 900 meters times 900 meters. From the visualization results, our model can extract most of the maps from both data sources. We release the correlative results from all fusion methods as a comparison in the same area. The IOU and actual visualization results can be clearly observed. Segments in red and blue show the difference between the prediction and the ground truth. This result shows our method, DeepDualMapper, in the left top corner performed the best. As an example, you can also see the entire map extracted by our model in the test area in Portal dataset. To demonstrate the utility of the gates, we perform experiments under different data qualities by making the information of one modality becomes noisy to simulate different data quality. As shown in the figures about the gate G, the first row is visualization of the data, and from left to right, data quality gradually decreases. The second and the third row are visualization of gate values. The second, GI, is for error images, and the third, GT, is for trajectories. More white pixels indicates a higher gate value, and more black pixels indicates a lower gate value. We can see that when the image fades and starts to lose more and more details, it gradually loses its confidence in prediction, while GI also gradually becomes smaller. We can find similar findings for the trajectory gates GT. Besides, in the last row, we can see the prediction is stable under different data qualities. As a critical challenge of map extraction is the information loss. We design a hardware experiment to test the robustness of DeepDualMapper. We conduct the information loss attack on testing dataset. In detail, we randomly remove the information of 1/4 area of the aerial image and another quarter area of the trajectory data. Then, we see whether the fusion model can correctly find out the right modality containing accurate information to perform the inference. The reported IOU demonstrates the robustness of our model. We give an example of the information loss attack to show the performance. As shown in the above figure, our model is the only one which successfully extracts all rows. Most of the baselines are vulnerable to the information loss attack. At the same time, our model, to some extent, can defend such attack. To further study how our model fuses the data and why it outperforms the other approaches under an information loss attack, we visualize the gate values computed by the gate fusion module from level 1 to level 5 in the bottom figure. We can observe that since quadrant 3 of the aerial image has been removed, the gate fusion module assigns higher weights to the trajectory data. Similarly, as quadrant 1 of the trajectory data has been removed, the gated fusion module detects that the aerial image carries more valuable information for the prediction. Accordingly, it passes the information of aerial images but blocks the trajectory information in quadrant 1. This experiment observed the change of the 4 feature maps AI, AT, AF, and AR during the entire decoding process. The right figure visualizes the predictions computed by these features from the first row to the fourth row in all 5 levels. We can observe the refinement procedure smoothes and connects the rows. The result is generated through the feature maps from coarse to fine, as well as from rough to smooth over 5 levels. The left figure is the quantitative results, which can also draw a consistent conclusion with our expectations. We put a Google group on this website and welcome all questions about the paper. We'll reply as soon as we can. You could also find this video there. Thank you for your attention.